Hello, my name's Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is Module 11 in our Circuits to Electronics lecture series where I talk about amplifiers and dependent sources and a bunch of concepts kind of related to amplification. So we're kind of now moving on to one of our next main topics in the course. So up until now, we've been talking a lot about transient and steady state response of circuits with resistors and capacitors. And now what I want to do is I want to switch gears a little bit and talk in the next few modules, 2 modules I think, about amplifiers. And we're going to start at from a fairly idealized place talking about amplifiers, and then we're going to get into some of the practical details of working with a non-ideal amplifier. And so, just as a starting point, amplifiers are often characterized as dependent sources. And as a definition, a dependent source is a source that delivers a voltage or current that is a function of another voltage or current. And so that seems a little abstract, but I think we can put some details around that. So typically the way that we draw a dependent source is using a diamond shape rather than a circle. So at least in this class, I will represent independent sources using circles, independent voltage or current sources. And remember, an independent voltage or current source is one that delivers its voltage or current no matter what else is happening in the circuit. A dependent source I'm going to represent as a diamond. We are only going to be talking about dependent voltage sources in this class. And our dependent voltage source delivers an output voltage, V0, and this V0 is a function of another voltage somewhere else within the circuit. And so somewhere else in the circuit, we've got, I'll draw this like this. We've got another voltage source. I'm going to call it V in. Call this V out. And V in basically controls the voltage of this dependent voltage source according to the following equation. The output voltage of the dependent source is equal to the input voltage, which is somewhere in our circuit, multiplied by a factor G. And G we are going to refer to as our voltage gain. So if G is greater than 1, the output voltage is greater than this input voltage. And we say that we've amplified our input voltage, right? We've made it bigger. That's what amplifiers do. And this allows us to increase the amount of power that we deliver to a circuit. And there's lots of different applications for amplifiers. So if we want to boost up a communication signal before we send it out some kind of transmitter, we'll use an amplifier. If we want to increase the volume coming out of a speaker, we will use an amplifier. So there's lots of different ways and places where amplifiers show up. Okay, so now let's consider 2 scenarios. In this first scenario, I'm driving a load resistor just with the input voltage. And in the second scenario, I'm driving that exact same load resistor with the output voltage of our dependent source. And this is sort of our, the no amplification scenario and then the amplification scenario. And so in this case, if we drive it just directly with our input voltage, the amount of power that we deliver to our load, and I'll just call this PI, is equal to V in squared divided by RL. Over here in the amplification scenario, the amount of power that we deliver to our load, I'll call PO, is equal to V out squared over RL. But of course we know from up here that our output voltage is just equal to our voltage gain times our input voltage. And so if we wanted to kind of quantify how much extra power we're delivering to our load thanks to our amplifier, one thing we can do is we can define something called the power gain. So the power gain, and I'll just call this GP, is equal to PO divided by PI. It's basically the sort of fraction of increase we see in the power delivered to our load thanks to incorporating our dependent voltage source or our amplifier. And so if we put in our equation, this is G V in squared divided by RL. This is V in squared divided by RL. RL cancels, V in squared cancels, and we end up just getting G squared. So in general, the power gain of our circuit or our amplifier is equal to the square of the voltage gain. So if we want to quantify how much extra power, the fraction of extra power that we're going to deliver to our load thanks to our amplifier, we just square the voltage gain of that amplifier. So the next thing I want to talk about is the unit of decibels. And decibels are something that we use a lot in electrical engineering. And it's probably something that you've even heard of a little bit, even before you came to engineering. And basically the reason why we use decibels is because in electrical engineering, we often deal with quantities that vary over a huge range. And a really good example is in a communication system. So for example, the signal that comes out of a wireless transmitter might have a power of about 1 milliwatt. That's kind of a typical value for sort of a Wi-Fi card or a cell phone. And but if you compare that to the received power of that signal, once it sort of travels through the wireless channel or down a wire, the received power is typically in the range of picowatts, right? So we go from 10 to the minus 3 to 10 to the minus 12 in a typical sort of communication scenario. And that's a huge difference, right? That's a huge range of values. And often, well, typically when we work with values that vary over a huge range, it's useful to look at them in a log scale because it tends to sort of blow up the smaller values and compress the larger values. And decibels, or more specifically bells, are units that just allow us to do this. And so a bell is the log of a power ratio. So whenever we're working with bells, we're always working with powers and we're always working with ratios. So a bell is defined as the log base 10 of two powers, P2 over P1. And that's the definition. And it's always a 10 base log. Don't use natural logs. And so what's a decibel? A decibel is just 10 bells. We often abbreviate decibels as dB, or we refer to them as dBs. But the definition of a decibel is just 10 times log base 10 of P2 over P1. Now, many of you might say, oh, I've heard of decibels before. Decibels are a unit used to tell us how loud a sound is, right? So we talk about, concerts being at a certain decibel level, or a sporting event, the crowd's making noise and you want to reach a certain decibel level. And it's true But the the actual definition of an audio decibel conforms to this ratio of powers. And so an audio decibel is just a measure of air pressures. So it's 10 times the base 10 log of P divided by 20 micropascals. And in this case, the P is the air pressure of the sound that we're measuring. And 20 micropascals is the air pressure that's sort of the threshold of our hearing. Any sound that makes a difference in air pressure of less than 20 micropascals, we can't probably hear it. Actually, most of us adults probably couldn't even hear 20 micropascals either. This is usually just very young kids who haven't been exposed to loud sounds can hear 20 micropascals. And just to show how incredibly sensitive the ear is, 20 micropascals is about 2 10-billionths of an atmosphere. So just sort of, it's like 2 10-billionths of the normal air pressure that we experience just walking around on Earth. So it shows just how incredibly sensitive our ears are. And so our ears can hear these incredibly faint sounds, but obviously we can register sounds that are quite loud as well. And because there's such a range of sound intensity, we tend to like to use decibels because it's on a log scale. So this is an audio decibel. We actually will be using audio decibels a little bit later on in the practical component of this course when we design a speaker amplifier. But for the purposes of the rest of this lecture, we're going to stick to using electrical powers, ratios of electrical powers in a circuit when we talk about decibels. And that's typically how most engineers use decibels, to express a ratio of electrical powers delivered to some kind of load resistance. And so just to work through a few very simple examples to get us kind of comfortable with decibels. Let's say, so we've got a ratio of two powers, P2 and P1. Let's say P1 and P2 are equal. Then obviously the ratio is equal to 1. Then 10 log 10 of 1 is equal to 0 dB. And so if our two power levels are equal, our decibel ratio is 0. Now let's say P2 is greater than P1. Let's say it's double. Then 10 log 10 of 2 is approximately equal to 3 dB. So if we have a circuit that doubles our power, then, or increases our power, then it's a positive decibel value. By the same token, if P2 is a half of P1, so if our power actually goes down, then our power ratio is equal to minus 3 dB. And so if our powers get bigger, our decibel units are positive. If they get smaller, our decibel units are negative. And you'll notice that, the numerical value of the dB unit is equal to just our kind of multiplying ratio. So if we go up by a factor of 2, we have plus 3 dB. And if we go down by a factor of 2, we have minus 3 dB. And you'll see this a little bit more as you work through a few more examples yourself. And so decibels are almost always used to define the gain of amplifiers. So let's say again we have our So we have our dependent voltage source, which will model our amplifier. We know that our power ratio, GP, is equal to the power delivered if we hook the output of our amplifier up to a load compared to the power we would get if we just hooked up our input voltage directly to the load without the benefit of the amplifier. And so this, we would call this a linear gain. So it has no units, it's a ratio of powers, so it would be a ratio of watts, and the watts would cancel. And we would say this is a linear gain. If I wanted to express our power gain in dB, I might sort of put a comma dB in our subscript, and it would just be 10 log 10 of our amplifier power divided by the power delivered without an amplifier, or in other words, 10 log 10 of our linear power gain. And so this is, typically when you look at, for example, the datasheet of an op amp, you'll see gain expressed in terms of decibels. And if you want to get the linear gain, you have to take the inverse of the decibel operation. So you move the 10 over, so you divide your decibel gain by 10, and then the inverse of the base 10 log is just taking your value and using it as the exponent of the number 10. And so this is how you would recover your linear power gain. And it's also the inverse of the decibel operation, if you like. When working with a dependent voltage source, it's also possible to find your power gain in decibels using just the voltage levels in your dependent voltage source. And so remember, our output voltage is equal to our voltage gain times our input voltage. And our power gain in dB is equal to 10 log 10 of our linear power gain. But we know that our linear power gain is equal to the square of our voltage gain. And our voltage gain is just equal to, I'll put that out there, the ratio of V out to V in. Now, there's a special property of logarithms. So if you have, log base 10, or really log base anything, a to the exponent, this is the same thing as just taking the 10 base log of a and then multiplying your result by n. So you can take this exponent and you can put it out front. So because of that, we can take this 2 and put it out front. And so our power gain in decibels is equal to 20 log times the ratio of our voltages. And that's sometimes handy if you're working with voltages instead of powers, or you don't want to if you're working voltages instead of powers. So we can take the linear ratio, but then we have to multiply, in order to get to decibels, we have to multiply by 20, just because we're taking our squaring exponent and putting it out front. Another thing that you commonly see in electrical engineering, for sure, is to use decibels to express a power level relative to a watt or relative to a milliwatt. And so I'll just show you what I mean. So let's consider a linear power P, which has units of watts. So if we took 10 log of 10 of P, which has units of watts, and we divided it by a milliwatt, which also has units of watts, these watts would cancel. And this would express our power level P relative to a milliwatt. And then we would say that we're expressing P in terms of dBm. And we add a little m there just because we want to make it clear that this is a power ratio relative to a milliwatt. If we wanted to express P relative to a watt, we would just go 10 log 10 of P divided by 1, right? Because we're, again, this is in terms of watts, this is in terms of watts, the watts cancel. And we would say this calculation expresses P in units of dBW. And so it's decibels relative to a watt. And you see this, there's a couple of different variations on this theme in engineering, in electrical engineering. When we express the, a power relative to a certain fixed reference point, we tend to add a little letter after the dB unit to indicate what our reference point is. So dBm is dB milliwatts, dBW is dB watts. Technically the audio decibels are relative to the 20 micropascals, as we saw. And so that would be another example of this type of decibel calculation, where we're showing a power level relative to kind of like a fixed baseline reference. And so anyways, I'm going to now kind of work through an amplifier example, and we can kind of get comfortable with not only this notion of dBm and dBW, but also just kind of using decibels in a calculation to determine the power level at the output of a system that either adds amplification to a signal or actually attenuates or reduces the power of the signal. Okay, so let's consider the amplification case first. So in this example, I'm asking you to determine the output power in units of dBm of an amplifier with a linear voltage gain of 30 and a 1 milliwatt input signal. And so I'm going to actually solve this question in two ways. The first way is going to be using mostly linear formulas, and the second way will be using mostly decibel or log formulas. And so let's start with the linear case first. So we know that our power gain is equal to the square of our voltage gain, and we know that our voltage gain is 30. So our power gain is 30 squared, or 900. We also know that power gain is equal to the power that we deliver to a load with the output of our amplifier divided by the power that we would deliver to the load if we just hooked up the input signal directly to the load with no amplifier. And our input signal, if hooked up to our load, would have a power of 1 milliwatt. Okay, and so these are the tools in our toolbox, I guess. And so we know that our output power is just equal to our power gain times our input power. And so we just substitute in our values. We've got 900 times 1 milliwatt, which gives us 900 milliwatts. And now I want to express that output power in dBm. So our output power in units of dBm is just 10 log output power divided by 1 milliwatt, right? Because it's relative to 1 milliwatt. So this is 10 log of 10, 900 milliwatts divided by 1 milliwatt, which is equal to 29. Let me double check that. Yeah, roughly 29.5 dB. And you'll notice here, you'll notice on the previous slide, I defined dBm as 10 log of power in watts divided by 0.001 watts. Here I'm just using milliwatts. And because it's a ratio, I can do it this way or I can do it this way. It comes out with the same answer, but just do that calculation yourself, convert everything to watts and do the calculation just to convince yourself that this doesn't change. And so that's our question, or that's doing our question in the linear domain. Now I want to redo this question using mostly decibels. And in this question, we're going to take advantage of the fact, or of a property of logs. So note that if we take the log of the multiplication of two numbers, a and b, that's equal to taking the log of a and then adding it to the log of b. So if you've got multiplication inside a log, you can just turn it into a summation. And we're going to take advantage of that. So in this sort of decibel part of the question, I am going to try to solve for our output in dBm directly. And so I know that this is equal to 10 log of 10 of our output power in milliwatts relative to 1 milliwatt. I won't put in the units there just so we don't get cluttered, but just understand that this is in terms of milliwatts. And we know that our output power is equal to our power gain times our input power. So this is equal to 10 log of 10 power gain times input power divided by 1 milliwatt. And we've got two quantities being multiplied here. And so I'm going to separate them out thanks to this property up here of logs. Okay, so we separate it out as a summation. However, this term is just our power gain expressed in terms of dB. This is just our input signal expressed in terms of dBm. And so we can write our equation that way. And this is a very common way that decibel calculations are done in electrical engineering. We know that, or when we've already got things in units of dB, we typically won't convert them back to the linear domain. We'll just add them together thanks to this property of logs. And so our input power in dBm So our input power is 1 milliwatt. We're taking this relative to 1 milliwatt, so this ratio is 1. So the units of our input power is 0 dBm, so it's exactly equal to 1 milliwatt. And our power gain in dB is equal to 10 log of 10 times 30. And if you do this calculation, you get 29.5 dB. And so our output power in dBm is equal to 29.5 dB plus 0 dBm, which gives us 29.5 dBm. And you might look at this and say, well, hold on a second. These units don't make sense, right? So I've got one quantity in terms of dBm, I've got another quantity in terms of dB, and I'm adding them together and I'm getting dBm. It's like we're adding amps to volts and getting amps. What's going on? Well, remember that basically this M here is just a little placeholder. It's just a reminder to remind us that we've taken the decibels relative to a fixed kind of reference power level. However, dBm is still just a plain old decibel calculation. So essentially, this has units of dB and this has units of dB as well. This M is just to remind us that we've taken the power in dBs relative to 1 milliwatt, but the unit is still in decibels. So basically everything here is decibels. This is just a little sort of placeholder reminder for us. And the same thing here. This is really technically in terms of decibels, but we've added this just to remind ourselves that we're doing all our calculations relative to 1 milliwatt. So go back in your notes, look at the definition of dBm, and then look at the general definition of decibels, and think about that a little bit and convince yourself that that's okay. Okay, this second example deals with signal attenuation. So electrical engineering systems don't always increase power, sometimes they decrease power. And a really common place for this to occur is when we transmit a signal, let's say some kind of communication signal, through a medium that attenuates it. So in this particular example, we've got a signal that has a half a watt power, a power of 0.5 watts, and it travels down a cable that attenuates that power by a factor of 1,000. And then the question asks you to determine the power at the cable output in units of dBW. And just incidentally, having a cable attenuate your output power by a factor of 1,000 is really, really mild attenuation. It's not uncommon for the power gain attenuation of a communications channel to be kind of on the order of 100 dB, which if you convert that back to linear, you'll find is 10 billion. So our output power is often 10 billion times weaker than the input power. So it really kind of gives you an appreciation for how amazing it is that our communication systems really work at all. So anyway, for this example, I want to do the same sort of procedure as the previous one. We're going to do it in the linear domain, and then we're going to do it in using decibels. In this case, our power gain has the same definition as for the amplifier. It's our output power divided by our input power. But in this case, it's 1 over 1,000. Right? So our power gain is less than 1 because we're attenuating our signal rather than amplifying it. So if we go through our linear calculation, our output power is equal to our power gain times our input power. In this case, we've got 1 over 1,000 multiplied by half a watt. and then we end up getting a half a milliwatt at our output. But we want to express our output power in terms of dBW, so that's decibels relative to a watt. And so our output power in terms of dBW is equal to 10 log 10 of 5 times 10 to the minus 4 watts divided by 1 watt, which turns out to be equal to minus 33 dBW. Okay, so now let's do the same calculation using decibels. And based on the previous example, we know that the output power in dBW is equal to our power gain in dB plus our input power in dBW. And we can just calculate these two quantities. Our input power in dB is equal to 10 log of 10, 1 over 1,000, which is equal to minus 30 dB. It's negative because our power gain is less than 1 rather than greater than 1. Our input power in dBW is equal to 10 log of 10, 0.5 watts relative to 1 watt, which is equal to minus 3 dBW. And so our output power in dBW is equal to minus 30 dB minus 3 dBW which is equal to minus 33 dBW, which is the same answer we got using our linear approach. So you'll get more practice with this on the assignments, but hopefully these two examples sort of give you an idea of how decibels work and how we can, we now have a couple different ways to determine the output power of our electrical engineering systems.